Hey kids, Mr. Webb here again. Um, we've been talking about simple machines and mechanical advantage, and so now we're going to talk about a wheel and axle. And basically, if you look at my example here, I've got one pretty much all set up for you. We've got our wheel out here, and it's a 20-inch diameter. That's what this symbol is here. So I'm going to go ahead and mark that because that may be kind of a new term for you. This is a diameter symbol. Okay, so whenever you see that, that means diameter. And we know that diameter is from here to here. Okay, so diameter is from one side of the circle to the other. And our axle, which is labeled here, is the center part of the wheel, and that has a 6-inch diameter. So if you look at the wheel straight on, this would be like if you were looking at this wheel, it would have the axle coming off of it. This is the axle, and this would be the wheel. So when you look at a wheel and an axle together, you're essentially looking at a lever, and what kind of lever this is depends on where the force is. If the axle is driving the wheel, you have the effort force here and the resistance force out here. If the wheel is driving the axle, then you'd have the effort force out here and the resistance force right here. Okay, so what I'm going to do is I'm actually just going to put a little weight here, and we'll kind of determine what we want this thing to be. Right now, this is going to be a wheel that is being driven by the axle. So as the axle turns, it is forcing this lever. It's an imaginary lever, it's not really there, but it's kind of forcing this piece, so our effort is being applied right here. Okay, so we have our effort force right there. And as it turns this, the outer wheel is being turned, but because it's there, it has resistance. So the resistance force is going to be right here. Okay, so there's our resistance force. And then what you would do is you actually would calculate this out. So we've got our forces here, and we may know this, we may not. But what we don't know is this guy right here. How far is the effort force from the fulcrum, and how far is the resistance force from the fulcrum? Okay, that's what we need to know. That's how we do our equation so that we can find the force times distance. Okay, so we've got these set up and we want to find these distances. Now we know that the IMA, the ideal mechanical advantage, is equal to the distance of the effort over the distance of the resistance. Okay, now I don't know how far this is, but I can go, okay, well it's half the diameter. The diameter is 6, so the distance of the effort I could say is the diameter of effort over the diameter of resistance, because we have the diameter is the same. I could also say that it's the same as the radius of the effort. Now the radius is our distance, so I could say that this one is equal to the radius of the effort over the radius of the resistance. Okay, that will give us the IMA. In this situation, it equals 3 inches divided by 20 inches. And so on our calculator, 3 divided by 20 is 0.15. Okay, so talking about wheel and axle with the AMA and the IMA, we have an example here. This is a little bit nicer than the one I drew. So we've got our same wheel, so we've got a 6-inch axle, we've got a 20-inch wheel, we have 200 pounds of force here at the axle, and we have 70 pounds of force at the wheel. And the question is, what is the actual mechanical advantage if the wheel is driving the axle? So here's the wheel, and it's turning the axle. So the axle is pushing back with 200 pounds of resistance, and the wheel is pushing up with 70 pounds of effort. Okay, so we look at our AMA, and our AMA says that our actual mechanical advantage is going to be the force of the resistance over the force of the effort. So the force of the resistance over the force of the effort is equal to, we know that the wheel is driving the axle. Okay, so the wheel is our effort. So we have 70 pounds. And the resistance is the axle. The axle is what's being driven, and that's 200 pounds of force. Okay, and when you calculate that out, you get 2.86. That is our AMA, actual mechanical advantage of 2.86. Okay. Now, if we looked at this same question from before, I actually think I had these reversed. If the wheel is driving the axle, what is the ideal mechanical advantage? Well, the ideal mechanical advantage is the distance of the effort, over the distance of the resistance. So the resistance was what? What was being driven? The axle was being driven. So we had 6-inch diameter, that means that's 3 inches. So the distance of the resistance is 3 inches. And that is over the distance of our effort. And the effort here was 10 inches. So if we take 10 divided by 3, we get 3.33. That is our IMA, our ideal mechanical advantage. So if we want to change the ideal mechanical advantage and the actual mechanical advantage into an efficiency, we know that efficiency is actual mechanical advantage over ideal mechanical advantage. So we have 2.86 over 3.33 for a grand total of 8.85. 858, which would be rounded to 0.86. Okay, if we convert that to a percentage, we get 86% efficient. Okay, so that's our efficiency. So we have the AMA here, we had the IMA here to solve for an efficiency of 86%. Now, why isn't it 100%? Well, we've got some friction from the tire and the axle, and maybe the bearings are going out. There's lots of reasons why. But anyway, that is how you would find your efficiency. And so there you have it. So basically, when we look at a wheel and axle, we just have a nice little lever. It's either a first-class lever, a second-class lever, third-class lever, depending on if you're driving the wheel or driving the axle. So if you look at it that way, it should be fairly easy to calculate out. Nothing's really different. This is actually almost exactly the same calculations as your lever calculations. So just make sure you know what you're doing here, whether the wheel's turning it or the axle's turning it, and you should be just fine. Okay, so don't forget, there are a couple questions that you may need to answer at the end of this video. We'll see you next time.